Okay, so we are going to carry on with worksheet 4 for alkane and alkenes. We have actually covered alkanes already. We have covered the general idea of what alkenes are. Now we're going to look at the properties of alkenes. Okay, so in this worksheet 4, we'll actually be looking at the physical and chemical properties of alkenes. So 1 and 2 deals with the two objectives here, or we call it the success criteria, deals with the physical properties. Okay, then the subsequent 3, 4, 5 deals with the chemical properties. Okay, chemical properties. Sorry, yeah. Okay, so these are what the things we'll be covering. Okay, so we'll state the 3 general physical properties of alkenes. Then we'll learn how to describe and explain how the physical property changes when going down the series. Okay, very similar to what we have done for alkanes previously. Then we're going to go on to look at the reactions for alkenes. Okay, combustion is actually covered in alkane already, so we're just going to do a quick one for alkenes. Then we're going to look at the new reaction called the addition reaction, which occurs for alkene. Okay, so we're going to learn to define what is addition reaction, and then from there we're going to state the 4 general addition reactions for alkenes. Okay, so let's start now. Okay, so for alkenes, the interesting thing is this. Okay, when going down the series, okay, so anyway, alkenes are covalent compounds. So they're actually simple molecular structures. If you remember, when you talk about bonding, right, we got ionic, we got covalent. And in covalent, actually, we got 2 main type. We got a simple molecule. Okay, so these are the small molecules like oxygen, nitrogen, O2, N2. And there's also what we call the giant molecular structures. Okay, giant molecular structures. These are like your diamond and your diamonds, graphite, silicon dioxide. So these are the 3 that was covered. So alkenes, they're actually covalent compounds with simple molecular structure. Okay, they're actually having simple molecular structure. So some of the physical properties that simple molecular structures have is that they naturally have low melting boiling point already. Okay. They also they cannot conduct electricity. Okay. Plus, we also know that they cannot dissolve in water. But can dissolve in organic solvent. Okay, these are the 3 physical properties that we learn in the covalent bonding, okay, about simple molecular structures. Okay, organic solvent. Now, in alkenes, we're just going to touch on the low melting boiling point, learning how to explain it a little bit. Okay, but we're also going to touch on the viscosity, and we're going to touch on the flammability. So we're not going to really talk about the conducting electricity. We're not going to talk about whether it can dissolve in water or not. Okay, all these are actually covered in your covalent bonding. The one we're going to elaborate a little bit more is the low melting boiling point, the viscosity, and also the flammability. Okay, those are 3 that we'll actually touch on a little bit more. So let's start. So going down the series, the melting and boiling point, okay, of the alkenes. So when you go from the first member to the second one to the third one to the fourth one, actually the melting and boiling point increases. Okay, so the melting boiling point is low. Okay, it's low in general. Okay, but as you go down the group, it will actually increase. Next one, going down the series, the viscosity also increases. When we talk about viscosity, we talk about the how difficult it is to flow. How difficult it is for the fluid to flow. Okay, so when you talk about how difficult it is for the fluid to flow, you can always compare your water and your oil. So water is considered quite easy to flow. Once you're on, you pour, it will just flow out like that, right? But when you pour oil, you realize it's thicker. It's actually harder to flow. Okay, so we say that high viscosity is like oil, low viscosity is like water. Okay, so that's the idea of what viscosity is. So in trend 1 and 2, we know that going down the series, the melting boiling point increase, the viscosity increases. So what's the explanation for it? So the explanation is this. So when you go down the homologous series, the alkene molecular size actually increases. Okay, the alkene molecular size increase. I mean, you just compare CH4 versus a this is alkene. So yeah, alkene is actually C2H4, C3H6. So you realize the number of carbons, the number of hydrogens actually increase. So the size of the molecule increase. Now, when the size of the molecule increase, okay, the intermolecular force of attraction actually also increases. Okay, so if the intermolecular force of attraction increases, hence more energy is required to overcome this force of attraction. That's why your melting boiling point actually increases when the molecule gets bigger. When the molecule gets bigger, the viscosity also increases because it's harder to overcome that force of attraction. So it's harder to flow. So this is the explanation for trend 1 and 2. Next one, going down the series, alkenes become less flammable. Okay, they become less, so it's harder to burn it. Okay, it's harder to burn it. So the question is, why is it harder, okay, for alkenes to burn? Okay, it's really because as the size of the alkene molecule increases, okay, the percentage of carbon in the alkene molecule also becomes higher, okay, or also increases. So when the percentage of carbon becomes higher, it becomes less flammable and it produces a smokier flame. Okay, so actually if the percentage of carbon actually becomes higher and higher, okay, when the chains get longer, actually the percentage of carbon gets higher, it's actually harder and harder for it to burn. Okay, one simple example I actually gave your friends was this. Just imagine your roads. Your roads are actually very long, very big alkene chains. Okay, so if the size is big and it's more flammable, all your roads now will be on fire, which doesn't make sense. So actually, the bigger the molecule, the less flammable it will become. Okay, once again, the bigger the molecule, the less flammable it will become. Okay, so these are the 3 trends that I need you to know. These are 3 trends I need you to know. Okay, and how to explain them is actually highlighted in green. Okay, highlighted in green over here. Ken, any questions so far? Thumbs up if okay, then I'll move on then. Okay, good. Okay, let's go. Next slide. Okay, so we are done with the physical properties part. Okay, sorry, I shouldn't go into this. So actually, we are done with the physical properties part. So, okay, so we can actually now do a tick for this. We actually will state the 3 general physical properties of alkenes. Okay, talking about the melting boiling point, viscosity, and the flammability. And we also learn how to explain their physical property changes. Okay, so that's actually what we've gone through. And now we're going to go into the reactions. Okay, we're going to go into reactions. So alkenes, like alkanes, actually undergo combustion reaction when react with oxygen. So in this question here, they ask you to write the balanced chemical equation for the complete combustion. Now we mentioned in previously, when you have a complete combustion, the 2 products that you're going to get is actually carbon dioxide and water. Okay, so what I'm going to do is I'm going to show you how to balance butane. Then you can try heptane. Okay, so let's, actually not heptane, this. Wait, didn't write wrongly. Can you all change this? This shouldn't be heptane. I want a heptene. Okay, go and change this. Instead of heptane, change to heptene. It should be a C7H14. Right, C7H14. Go and change it. Okay, so for butane, okay, so it's a C4H8. Because combustion is actually the reaction with oxygen. So plus oxygen. What I'm going to get is carbon dioxide plus water. So this is my chemical equation. Now I need to balance it. The order that you're supposed to balance is carbon, followed by hydrogen, followed by oxygen. So this is the order that I need you to balance it. So what I'm going to do is, I'm going to show you how to do it. I'm going to use blue to indicate the balancing. So I got 4 carbons on the left-hand side. So I'm going to CO2, I'm going to put 4 over here. Okay, because the only way to increase number of carbons on the right-hand side is through the carbon dioxide. Next thing, I got 8 hydrogen. So the only way to increase hydrogen on the right-hand side is to change the water. So I'm going to put a 4 here. So this will help me to balance my carbon and my hydrogen. Then the last step is to balance the oxygen here. So I got 4 O2, so 8 oxygen here, plus another 4 from over on the right-hand side. So total 12. So I need to put a 6 over here. Okay, so this is the balanced chemical equation for combustion for your butene. Okay, so what I need to do is I'm gonna write the chemical equation for you for heptene. I want you to balance it. So heptene is C7H14 plus O2. It will give me CO2 plus H2O. Okay, so I want you to just take some time now to go and balance it. So maybe take about the next 2 minutes to go and try balancing it. Okay, I'll pause the recording up so I can carry on. Okay, so let me balance the equation now just to help you all check whether you've gotten it correct. So let me use blue over here. So I got 7 carbons, so I'm going to put 7 over here. I got 14 hydrogen, so I'm going to put 7 over here. So we have 14. Then you realize on the right-hand side, 7 times 2 is 14. 14 plus 7, I got 21 oxygen. So how to get 21 oxygen? Actually, I'll need to have a 21 over 2. Okay, 21 over 2 to get 21 oxygen here. But of course, you know that balancing equation, you cannot write 21 over 2, right? Okay, there's no fraction really indicated. So if I want to have fraction, it'll be 1 C7H14, 21 over 2 oxygen, 7 CO2, and 7 H2O. But this is not correct because we will not leave it in fraction. Hence, what we're going to do now is we're going to remove the 2 at the bottom. So across the whole thing, we're going to multiply by 2. Hence, what I'm going to write in purple here will be the correct answer. So if I multiply 2 throughout, it will be 2 C7H14, 21 O2, 14 CO2, and 14 H2O. Okay, so the one in purple is the correct balancing numbers. Okay, correct numbers for the balancing of equation. Okay, so I hope combustion, okay, at least you realize that writing this equation, you're getting a bit more used to it already because we did it in alkane. We have done it now in alkene. Okay, next. Let's go on. Okay, we're going to go into the next reaction here. Now, the next reaction we're going to learn is a more generic version for now. So we know that alkanes undergo substitution reaction. Okay, sorry, why am I highlighting here? Okay, alkanes undergo substitution reaction. But for alkenes, they actually undergo what we call addition reaction. Okay, addition reaction. So what exactly is addition reaction? Okay, what exactly is addition reaction? So an addition reaction is a reaction, okay, of course it's a reaction, right? In which an unsaturated organic compound, okay, combined with another substance to form a single new compound. So what exactly does it mean? So addition reaction is a reaction in which an unsaturated organic compound, what is unsaturated? Is actually an organic compound that contains this C double bond C. Okay, so what homologous series contain this C double bond C? You know, is your alkenes. That's why your alkenes undergo addition reaction. And when it combines with another substance, it forms a single new compound. So I'm going to show you via a reaction here to help you understand what it means by having a single new compound. So let's have a generic alkene. So alkene reaction, when we talk about addition reaction, we will actually focus on the double bond. Okay, we'll focus on double bond. Now, so I have my double bond here. Okay, so this is actually my alkene. What I have at these 4 corners could be anything. Could be extension of carbon of hydrogen or whatsoever. But I just leave the 4 there as a gap because my focus is on the C double bond C when the reaction is happening. The rest of the other parts will not react. Okay, so I'm not going to be fussy over what's at the 4 corners there in this general equation. So the C double bond C is the one I want to focus on. Okay, it will react with another substance. Typically, we can identify that substance. Imagine it's like an X and a Y, okay, bonded together. X and Y bonded together. So when we have an addition reaction, means that these two will actually plus together. Okay, what we're gonna get. Okay, what's happening here? So I'm gonna draw for you what's happening. So I'm gonna use a different color. I'm gonna use maybe black. So when X and Y approaches this C double bond C, what happens is that one of the double bond will actually break. Okay, so I indicate here will break. The bond between X and Y will break. And what happens is that because now the two carbons here are short of one bond, right? They will attach like this. So the black actually shows you the mechanism of what's happening. It shows you the steps of what's really happening. Okay, so let me recap, say it again. Okay, so sorry, I realize my arrow gone. Okay, so I'm going to show in black again. So when X and Y approaches the C double bond C for the addition reaction, what happens is that the double bond, one of the bond will break. The bond between the X and Y will break. Then the carbon will attach to one of the atom. The other carbon will attach to the other atom. Okay, so this is the mechanism of what's going to happen. I'm going to erase it all now because this is not part of the equation. This is just showing you the steps that's happening. And hence, when this reacts, what I'm going to have is C, single bond C. Okay, I still have my same four groups at the top and at the side. So you can see we rearranged a little bit. Okay, I actually made the bonds go upwards and towards the side. At the bottom, I left it for X and Y. So X and Y, what's going to happen here? I'm going to use black to show you. So X will be connected here. Y will be connected here. So the bond between the X and Y will actually disappear, and they will actually form a bond with the carbon, okay, with that double bond initially. So this is an addition reaction. Okay, so what are the specific addition reaction? Well, this is the general equation. This is the general one, okay, of what's happening. We will go into the specific now of really what is being added to the alkene. Okay, what is being added to the alkene. So there are four main categories that can happen. There are four main addition reactions that can happen. So addition of hydrogen. So we can actually add hydrogen to the alkene. We call this hydrogenation. Okay, we can also add bromine. Okay, normally we add bromine, we're actually adding bromine solution, or we can actually call it aqueous bromine. Okay, when you add aqueous bromine or bromine solution, this reaction is actually called bromination. Okay, so there's addition of hydrogen, we call hydrogenation. Addition of bromine, we call bromination. The other one is addition of steam. Steam is actually your water molecule. Okay, just as in the gaseous form. We call this step, because you're adding water to the alkene, we call it hydration. And the last one is the addition of the alkene molecules themselves. So we can add more alkene molecules to one another. Okay, this reaction we term it as addition polymerization. Okay, addition polymerization. So we're going to go through this four reaction in the next worksheet. But just want to highlight one thing which I just now mentioned. Okay, it's really to understand what this whole addition reaction is about. So we say that addition reaction is so we are down here. So we say that addition reaction is a reaction in which an unsaturated organic compound, the C over here, combined with another substance. This another substance is like the XY they have drawn at the bottom here, to form a single new compound. So you can see over here in purple, do you realize this is the only, again, this is the only compound that is formed. So this is the single new compound. Okay, there's no other things that's being formed. Don't have. No other things being formed. So that's why you just add in and you form a new molecule. Okay? Any questions for this part? Thumbs up if okay. Now move on. Okay, good job. So what we have done, we have actually learned how to write the equation for combustion reaction. We have defined what addition reaction is, and we have stated the 4 addition reactions that you need to know. Okay. Now the conditions we'll actually be covering later, but at least now you know that alkene undergo addition reaction. There are 4 main ones that you need to know, which we have written here. That is hydrogenation, bromination, hydration, and addition polymerization. Okay, so let's go on to worksheet 5 now. Let's press on. Okay, so in this worksheet, we're going to cover all the reactions, all the reactions. So you can see hydrogenation. We're going to cover bromination. We're going to cover hydration. And last one, we're going to cover, okay, addition reaction of alkene with alkene molecules. This is actually your addition polymerization. So we're going to go into each of these reactions in detail. Okay, we're going to go into each of these reactions more in details. So let's start. Okay, hydrogenation is an important process that converts alkenes to alkane. I want you to highlight this part here. This is important because actually hydrogenation converts your alkene into alkanes. Okay, it's also part of the process to cause your unsaturated fats to become to convert your unsaturated fats or oil molecules to become saturated. So hydrogenation not just only deals with your alkenes becoming alkanes, they actually convert the unsaturated segments of your oil and fats to become saturated. Okay, saturated actually means that there's no more C double bond C. Okay, so all of these has been reacted away to become your C single bond C. Okay, so all reacted away to single bond C, that's why there's no more. Can? Now, so back to question. What are the conditions for hydrogenation? So in organic chemistry, you realize there's this idea of conditions. Okay, that means in order for the compounds to react, okay, for the substances to react, you need to give it a certain temperature, maybe even with a catalyst or pressure. So the 3 things we always consider is temperature, pressure, catalyst. In this case, for hydrogenation, okay, the conditions only deals with temperature and catalyst. So what's the condition? It is 200 degrees Celsius and nickel as a catalyst. Okay, it's actually 200 degrees Celsius with nickel as a catalyst. So we're gonna now write the chemical equation. So I'm gonna show you how to write the balanced chemical equation, showing the full structural formula for the addition of hydrogen to ethene. So ethene is C double bond C, H, 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 H. So this ethene, a 2-carbon alkene. Now you realize I purposely arrange my hydrogens towards the top and towards the sides. I leave my bottom empty. So for addition reactions, I always leave my bottom empty, okay, of my C double bond C. So that is easy for me to visualize what's going to happen next. What I'm going to do is I know hydrogenation is to add hydrogen. So hydrogen, this is the structural formula. Okay, 2 hydrogen bonded with a single bond. Now, because this is organic equation, so you need on the arrow your conditions. So 200 degrees Celsius and then nickel as catalyst. So once I've added to the bottom, you realize that for my ethene, once hydrogen is added, okay, I'm going to show you the 2 hydrogens that I've added using a different color. So I'm going to use purple. So what I've drawn here is with the double bond broken, and a new bond is 2 new bonds are formed downwards with the hydrogen over here. So you can see the hydrogens are added to the different carbons. So take note, addition reaction occurs, okay, and each of the atom is added across the 2 different carbons. Okay, I say again, each of this atom is added across the 2 different carbons. You will not, I say again, you will not have both hydrogen attaching to the same carbon. So take note of that. Okay, you'll see it clearer in the subsequent, in hydration. Okay, you'll see it more clearly in hydration. Okay, so what I want us to do now Okay, there's some practice. I want you to try it out. Go to slide 22, I think. You go to slide 22. Okay, with what you have on the previous slide, which is slide, sorry, I forgot my slide. Okay, on the previous slide, you have copied down this equation, right? Part B, right? On slide 18. Okay, with this equation on slide 18, I want you to refer to it and try to do question 1 and question 2, okay, on slide 22. Okay, so I say again, I'm going to give you all some time, maybe about 3 minutes, to go and try question 1 and question 2 to practice on the drawing. Okay, to help you all a little bit, because some of your friends also struggle with what is 2-methyl-butene. So I'm just going to draw the 2-methyl-butene for you. Okay, first thing for 2-methyl-butene, I'm going to draw the butene first. So this is the first step. So butene means I got 4 carbons. The double bond is on the second position. Okay. The methyl is on the second carbon, 2-methyl. So I'm going to have a methyl group, that means a single carbon attached out from the second carbon over here. Okay, so this is the step 2 that I did. So I draw the butene, the general carbon chain. Then I know I have a single carbon branching out from carbon number 2. So this is how it looks in terms of what we call the carbon skeleton. Then I will now fill it out with H. Okay, just have to make sure that all my carbons have 4 bonds. And you realize I purposely left the bottom part of the C double bond C empty. So I'm going to highlight here in green to show you. I left this whole part here empty, okay, so that I can do my addition properly. Okay, so this is 2-methyl-butene. Okay, propene, I think you all should be able to do it's a 3-carbon alkene. So I give you all now till 11:10, okay, to go and draw this two. Okay, so 3 minutes to go and try it out. Okay, so I'm going to pause the record. Okay, so for the first one, propene, addition of hydrogen. So I'm going to draw my propene here. So it's a 3-carbon chain. Propene, so I need a C double bond C. Then after that, I'll just complete to make sure all my carbon has 4 bonds. So how do I ensure all my carbons have 4 bonds? I'll let it bond to H, hydrogen. I know that this one, I'm going to add hydrogen to it. Because this addition of hydrogen, so it's hydrogenation, I need to write the condition, 200 degrees Celsius. Okay, nickel as my catalyst. Then my final product, okay, so this is my propene. Once I've added hydrogen in, okay, I'm going to show you how it looks. Okay, so you realize I purposely left the bottom empty, so I can use a different color to show you where the addition has occurred. Okay, which is to the left-hand side, the 2 carbon over there, where my double bond was originally on. So I can use yellow to show you these 2 carbon were the original one with double bond. These 2 carbon here are the ones with double bond previously. So you can do the comparison. Okay, and this fella here now is actually my propane. So you can see here from an alkene, it became an alkane. Okay, so that's actually what hydrogenation does to my alkene. It converts it to an alkane. Next one, so I got this 2-methyl-butene. I'll let it undergo hydrogenation. Okay, so once again, my arrow, I need to have that 200 degrees Celsius, nickel as my catalyst. So what I'm going to get, I'm going to add to the bottom. So I'm going to draw my main structure again. Okay, at the top here, I got CH, H at the top, CH, CH, H. So I'm going to use yellow highlighter to just show you where's the original 2 carbon with the double bond. This is the 2 carbon with double bond. And after I've added in, okay, the hydrogen will actually be over here. Okay, so this has now become an alkane. What is the exact name of this alkane? actually you don't need to know the naming convent, don't need no naming lah, but I'm just going to write it down for you. This is actually a 2-methyl, okay, butane. Alright, this is actually 2-methyl butane. Right, the naming, as I mentioned, you don't even know, you only learn this when you go to tertiary education. Okay, so just take note of it. Okay, let's return back to slide 18. Enough of these examples that we've gone through already. Let's carry on with hydrogenation, a little bit more on the application part. Okay, so we talk about addition reaction, you know that the double bond is important. So what exactly happens at the double bond part, right? So let's look at it a little bit more. So vegetable oils are considered polyunsaturated. As I mentioned, alkenes, okay, they contain a C double bond C, that's why they're unsaturated, right? So vegetable oils are considered polyunsaturated is really because they contain C double bond C. So the unsaturated part tells you about C double bond C. How about the word poly? Poly means what? 2 or more. So if I were to combine these two, okay, okay, so what exactly is polyunsaturated? Okay, so polyunsaturated, okay, means that the compound contains 2 or more carbon double bond. Okay, they contain 2 or more carbon double bond. Okay, this is the one that we're looking at, the carbon double bond. Okay, so polyunsaturated means that they contains 2 or more because of poly. Unsaturated means that there's that carbon double bond. Okay, so vegetable oils are polyunsaturated, so they are oils. Then of course, what's the difference between oil and fats, right? So I mentioned that oil, okay, is a liquid. Typically is a liquid. While, okay, so if you look at this, if I say it's a liquid, so I'm comparing the states of matter, right? So if oil is a liquid, if I want to compare it with fats, so while fats is a solid, okay, sorry, our fats are solids. Okay, oil is a liquid, oils are liquid. My English. So oils are liquids, while fats are solids. So it's really the states. Okay, so if you got more unsaturation, okay, if you got more unsaturation, you're gonna it's gonna behave more like a liquid. If you have it more saturated, it's gonna behave more like a solid. Okay, in terms of comparing the fats and the oils kind of concept. So how can I convert vegetable oil into solid margarine? Solid margarine actually is like, imagine it's like fat lah. So oil, how to convert the liquid into a solid? How to convert the vegetable oil, which is polyunsaturated, into a solid margarine, which is the saturated one. So the process we'll be using is actually what we've gone through. Okay, it's actually let vegetable oil, okay, undergo hydrogenation. So if you use hydrogenation to react with vegetable oil, okay, it will actually cause it to become solid margarine. So take note, if you want, you can kiasu a bit, write the condition. Okay. Condition over here. To convert the unsaturated to saturate iron. So you can let the vegetable oil undergo hydrogenation, not to convert, to cause it to become saturated. Okay. So the unsaturation is gonna become saturated. Okay, so that's what they do. They actually do hydrogenation to convert all my C double bond C into C single bond C, okay, by doing hydrogenation. Okay, so this is for hydrogenation. Any questions so far? Adding of hydrogen? Kieran, Joris, Janine, all okay? Okay, good. Okay, thumbs up. Let's go. Okay, now we're going to go on to the next part, which is bromination. Okay, so what exactly happens during bromination? Now, some context to note. So the solution of bromine is actually reddish brown. So a solution of bromine is reddish brown, like what you can see here. Okay. When alkene is added to a solution of bromine, the solution turns from reddish brown to colorless. Okay, so you can see the solution turns colorless. Okay, so this is actually quite interesting here because bromine is reddish brown. When it turns colorless, you realize there is an observable change. There is an observable change. And because there is an observable change, it means that I will be able to distinguish things through a reaction. Okay, because there are things I can watch. If it causes a color change, it means it must be something. If it doesn't cause a color change, it means it is another thing. Okay, we're going to go a little bit more into detail about that in the subsequent question. So, but first, let's start. What is the condition required for bromination of alkenes? Okay, what's the condition required for bromination of alkenes? Now, hydrogenation, 200 degrees Celsius and nickel. So you must heat it up, must add nickel for it to react. But bromination is actually interesting because there isn't really any condition per se. You can just let it react at room temperature and pressure. So at normal condition, which is our normal room temperature and pressure, it will react. So we call this RTP, room temperature and pressure. So bromination can occur at your normal room temperature and pressure. So I'm going to write the balanced chemical equation to show you the addition of bromine to ethene. So once again, okay, this is ethene. I'm going to add bromine to it. So bromine looks like this. Okay, single bond, single bond. On the arrow, don't need to write anything. Okay, so what's going to happen? My bromine is going to add through the bottom. And this is the new compound after addition. So I'm going to use blue to show you where the bromine has added. Okay, so the name of this initially is called ethene. After addition, okay, there's no more double bond, right? I got two bromine, each one added to different parts. So this is actually called a 1,2 dibromo ethane. Okay, the 1,2 dibromo tells you that the bromine is attached to the first carbon. Another bromine is attached to the second carbon. So they're attached to different carbon. So I will say again, the 2 bromine, okay, is attached to different carbons. Can? So just take note of that. Okay, so this ethene has been converted to a 1,2 dibromoethane. So the bromine is added to 2 different carbons. Now, based on this, once again, we're going to do a little bit of practice. I want you to have a sense of how the reaction works, how the addition really occurs. So we're going to go back to slide 22. Okay, I want you to try now question 3 and question 4. But this time around, I'm going to show you because pen 1 in, okay, you don't know how to draw, so I'm going to draw the initial thing for you. So how does the pen 1 in look? Pen 1 in looks like this. So pen actually tells you 5 carbon. So I'm going to draw 5 carbon as a chain. The double bond occurs on the first carbon. So this is the carbon chain for pen 1 in. Then I'm going to draw hydrogen, okay, to just fill up. You realize once again after drawing like this, my bottom part here is empty. Okay, so maybe I should use green color. Okay, the bottom part here is empty. Okay, so I can do my addition. I'm going to help you draw this 2,3-methyl but1 in. Okay, how exactly to draw this? I'm going to draw but1 in first. So 4 carbon. 1 in tells you that the double bond is on the first carbon. Okay, E and E tells you there's a double bond. So 1 tells you the position of the double bond. 2, 3 methyl, that means there's a methyl stands for 1 carbon branching out. So there's 1 carbon branching out on the second carbon. There's another 1 more carbon branching out on the third carbon. Okay, so this is actually your 2, 3 methyl butane. Okay, now once I've drawn the carbon frame, I can actually now just write my hydrogen in. Okay, so I'm doing this just to help you to be able to draw your, to do your reaction so that you're not so hard up on really what exactly this 2,3 methyl butane is. Okay, and you can see here, I left the bottom part here empty for you to do your bromination. Okay, so I'm going to give you all now till 11:26, about 3 minutes. So you all can go and try now to do the 2 questions. Okay, so I'm going to pause the record. Okay, so we should have some time to have drawn the thing. So I'm just going to go through it right now. Okay, so this is your pen 1 in. We're going to add bromine to it. Your arrow now doesn't have any condition on top because it's at room temperature and pressure. So I'm going to draw the exact same thing here, except that the double bond is going to disappear. Okay, 1, 2, 3, 4, 5. Okay, so I'm going to draw all the H that's present. Okay, why so leche? I must draw all the various bonds because I want it as a full structural formula. Okay, so once I've done this, you realize that, okay, once again, my carbon, the initial carbon here, okay, my double bond broke. I have the double bond broken. I'm going to add the 2 bromines here. So bromine to this, bromine to this. Okay, so you can see once again the 2 atoms are added across different carbons. That's one important thing you must be able to take note and spot. Okay, so this is for the pen 1 in after you have added bromine to it after bromination. For the bottom one, the 2,3 methyl butane in, actually you realize no matter how chim the molecule looks, how difficult it looks, your focus is always at where the double bond is. Okay, so I'm going to add bromine now to here. Arrow. So this one is a super leche big molecule over here. So I'm just going to draw it out. So I got 4 carbons. I'm going to have 1 carbon attached out here, 1 carbon attached out here. So I'm going to draw my H, 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 H over here. Okay, so almost done. Yes. I'm going to once again highlight in yellow. This is where my C double bond C is. After I've added my bromine, okay, this is where my 2 bromine will go to. So you realize the reaction actually is not very difficult. Your focus is just on the C double bond C. Okay, your focus is actually just on the C double bond C. Okay, so this is actually your bromination here. Let's go back to slide 18 to just complete my slide 18 over there. Sorry, not slide 18, slide 19. Okay, so how can I distinguish? So we have done enough bromination already. So we have reacted, we have learned how to write the chemical equation. We know where bromine is added to the various compounds, which is on the C double bond C. So one of the application of bromination. So part C actually is looking at the application, okay, for bromination. So how can I apply bromination? How can I apply bromination? Is it really a helpful process that I need? Okay, answer is yes, it can be a very helpful process. Because why? Alkane is saturated. You realize that there is no C double bond C. Whereas for alkene, it is unsaturated. So there's C double bond C, right? So how can I distinguish between them? Key idea, bromination. So I'm going to add bromine solution to them. Add bromine solution to alkane, to de-alkane and alkene separately. Okay. So now what's going to happen? Okay. For alkane, for alkene. Okay, we're going to start with alkene first. For alkene, comma, the bromine solution will turn from reddish brown to colorless. Oh, sorry, spell wrongly, colorless. Okay, to colorless. So alkene will actually cause the bromine solution to turn from reddish brown to colorless. So you can see an observable change. Okay. Whereas if, okay, so I'm going to write blue now, for alkane, the bromine solution will not have a change in color. Okay, so the bromine solution will remain reddish brown. So that's actually how you distinguish between your alkane and alkene if you have them mixed up. Okay, ready? You just add bromine solution to a small sample of it. The bromine solution will turn from reddish brown to colorless for alkene. If it's an alkane, the bromine solution will remain reddish brown. So that's actually how you distinguish. Okay, because for alkene, there is an observable change. Whereas for alkane, I'm going to write in blue, for alkane, there's no observable change. Okay, your bromine solution remains reddish brown. So there isn't an observable change. So bromination is used to distinguish between alkene and your alkane. So just take note of that. Okay, that's how they distinguish between them. Okay, so that's for bromination. Any questions so far? Thumbs up if all okay. Okay, thumbs up, good. I'm gonna carry on now. Okay, so we are done with hydrogenation. We are done with bromination. We are now gonna go into the next one, which is called hydration. So alkenes and alcohols are different homologous series. However, alcohols can be produced from alkenes using hydration. So alkenes, if I let them undergo hydration, I can actually get my alcohol. Okay, so this is what we're going to look at this process. How can we get alcohol from alkene? The thing here we're going to use, the process is going to be called hydration. So what exactly is hydration here? It's actually the addition of steam, right? So what's the condition? This time around, we got all three conditions: the temperature, pressure, and catalyst. So the condition is 300 degrees Celsius, 60 atmospheric pressure. So it's actually quite a high pressure. And we got to use phosphoric 5 acid. Okay, phosphoric 5 acid. So just take note, the V, the 5 over there is important. Okay, now, so what happens really during the addition of hydration of alkenes, right? So we're gonna do addition of water. Okay, actually it should be steam to ethene. So ethene is C double bond. I should be using red. Sorry, let me use red to just be consistent with the color scheme. So ethene, C double bond C. I put my H on the top and at the side. I'm gonna add steam here, which is water. Now I want you to see this. Water actually is H2O, right? So I'm gonna draw it like this. Okay, I'm gonna draw it like this, and I'll explain to you why later. Okay, so I'm gonna draw it like this. So water. I'm gonna have on my arrow the condition. So 300 degrees Celsius, 60 atm. Now I'm gonna have my phosphoric 5 acid. Okay, in the addition reaction, so once again, my ethene, I'll break the double bond to become like this. Now, for the water, what's exactly going to happen? Okay, I'm going to highlight two parts here. One part in light green. One part I'm going to highlight in purple. Okay, I want you to see green as one group, purple as another group. Hence, if I were to look at it like that, the bond which I'll be breaking is actually this bond over here for water. Okay, so once I break this bond, you realize that, okay, how will the whole thing attach? The carbon on the left-hand side will be attached to the hydrogen. The carbon on the right-hand side will be attached to the oxygen, which is attached to the hydrogen. So you can see here, where's the highlight? Green, purple. Okay, can you see the two groups that's being added to the different carbon? One is a H, the other one is a OH, okay, being added to the carbon. Now, the interesting thing is this. My water doesn't mean, when I add water, right, it doesn't mean that my molecule must always look like this. Okay, you realize that I can actually invert the other way around. So instead of adding HOH, or your water being arranged like this, it could also look like this. Right, you can see I can actually add it like this. Okay, so maybe let me use consistent use red color again. So I just want to show you that actually I can change the position of my water. Instead of HOH, I can draw it like that. Okay, I add it to ethene. I want you to see that because I've rotated the water, the position looks slightly different. Okay, so the condition I just put dot, 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 you can just imagine it's the same thing on the right. So if I've done this, okay, I'm going to draw the basic structure again of my product. Now I'm going to show you where the green goes to. Sorry. I'm going to show you where the green goes to and where the purple goes to. Okay, so once again, the same thing, the bond that I'm going to break is this one over here. This is a bond I'm going to break. So my OH now, instead of at the right carbon, I'm going to attach it here. Okay, because of the positioning that I've done. Can you see this OH now is on the left-hand side? Then the H is actually on the right-hand side. So you can see that because of the rotation of the molecule, my OH now is on the left-hand side. My H now is on the right-hand side. So it seems like there are two possible products because of the position where I've added the OH. Okay, I just want you to take note of that part over there. Okay, so now with this, once again, we're going to go into a little bit of practice just so that you have a sense of really what's happening again. So I want you to look at, let's see whether there's anything. Nope. So go to slide 23. Okay. I want you to draw for me, okay, the addition of steam to propene. Show the two possible products that can be produced from this addition reaction. Okay, so go and try this one out now. Okay, go and try only question 5. Okay, only go and try question 5. So I give you about 1 minute to go and try it out. Okay, maybe 2 minutes. 2 minutes going to try it out. Okay, so I'm going to pause the recording now. Continue here. So I've drawn the propene out already. So I'm going to show you after you have added steam. Okay, so I'm going to draw the water molecule out. I'm going to show you that there's two possible ways to add it. So I'm going to draw the two possible configuration of water. Okay, one of them is like this. The other way you can draw it, it will look like this. Okay, sorry. Maybe I should just use a lighter red. Let me use a different red. Maybe I use orange. Okay, because of the orientation of how I'm drawing the water molecule. Okay, so actually I can have two different products. So I'm going to draw arrow here, 300 degrees Celsius. Please make sure you have your conditions all drawn in, all written on the line. Okay, phosphoric 5 acid. So if I were to use the top one, so let's say the first one, okay, my product will look like this. So I'm going to have carbon, my 3 carbons here, H, 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 H over here. So just to show you where my double bond is initially, I'm going to use highlight in yellow like what I did previously. Okay, so you can see that's where it is. Now, for my water, I'm going to show you how I'm going to split it up. So OH, and I'm going to use purple, H. Okay, the bond I'm going to break is the one between the green and the purple. So my new product here will be OH on the first carbon, H on the second carbon. Highlighting in green here to show you where the groups have attached accordingly. Okay, so this is the first product that I can get. Okay, this is the first product I can get, the first product. Now I'm going to draw for you the second product. Okay, the second product that I can get. So you must be able to see how you're going to split it up again. So I'm going to use green and purple highlight to show you what is going to the left and what is going to the right. Okay, the bond between the green and the purple is the one that's going to be broken. So I have my 3 carbon again, and I have my H like this. Okay, this time around, I'm gonna have my H attached to the left hand side. I'm gonna have my OH. Oh, sorry, I realized I have to draw more hydrogen here. Okay, I'll say again, I'm gonna have my H attached to the carbon on the left. I'm gonna have my OH attached to the carbon on the right hand side. Okay, highlighting once again in green and purple to show you what is on the left and what is on the right. Okay, the difference. Now you say, Che, this one, what's the difference? The naming itself is very different already. Okay, this OH is attached to the first carbon. So actually, we will call this propan 1-ol because the OH group is attached to the first carbon. Now you can see here the OH group is attached to the second carbon. So actually, this is called a propan. Sorry, propan 2-ol. Okay, propan 1-ol, propan 2-ol. Okay, so these are the 2 possible products. Actually, key idea here is OH and H. Think of it as 2 separate groups added to the different position. Hence, for question 6, you realize this one look very cheap, right? You see me is the 3-methyl cyclohexene. It's just this thing that you see here. Okay, but most importantly, when you talk about addition reaction, talk about hydration, right? My focus is always on the double bond. The rest of the molecule will stay the same. So I want you to now take the next 1 minute to draw the 2 possible products from this. Okay, your focus is on the double bond. What do you think are the 2 possible products that can come out from this? Well, it takes 1 minute now to go and try it out. Okay, I'm going to pause the thing again, the recording. Okay, so what are the 2 possible products from the hydration of this thing here? As I mentioned, your focus is just on the C double bond C. The rest of the molecule you can actually just ignore. Hence, what I'm going to do, I'm just going to redraw the whole molecule out again. So CH3 attached to a CH. Then you can see like this is like a hexagon here. So CH2. And I'm going to draw exactly the same as it is. Okay, CH2, 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 CH, single bond, CH, single bond. Because you know that after you have hydrated it, the double bond will break. So that's why I got my single bond here. Now, you know, one of them is going to be a OH, the other one is going to be H. So I'm going to do, I'm going to attach the OH to the top. I'm going to attach the H to the bottom. Okay, so this is the first possible product. The second possible product will look like this. So I'm going to draw once again the same skeleton. Okay, the same skeleton out again. Looking exactly similar to what I've drawn on the left-hand side. Okay, except now, instead of the OH being on the top, I'm going to put the OH at the bottom here. At the top, I attach a H. So you can see I've swapped the position of the H and the OH. That's how I get the 2 different products after the addition. Okay, so just take note of that. Okay, so this is for slide 23 on the possible products after hydration. So let's go back now to slide 19. Okay, so we're done hydration here. Next slide. Okay, part C, I think this one you all do as your additional practice. I'm not going to go through what the answer for this is, but this is just to let you know, after going through the examples we have shown you, how to exactly draw the possible hydration products of your propene. Okay, so you draw a propene out first, then after that you add the H and the OH separately. Okay, so this marks the end of the hydration. Hence, what we have covered so far, we have covered hydrogenation. We have defined the term polyunsaturated and know what's the difference between oil and fats. And we have actually sort of like stated how margarine can be produced from vegetable oil, okay, which is hydrogenation. So these whole three things here deal with hydrogenation. Next, we did bromination. So we learned how to describe how bromination occurred. Okay, and we mentioned how we can use bromination to test whether it's an alkene or alkenes, okay, whether it's saturated or unsaturated. So these two deals with bromination. And what we have done next is actually to do hydration, okay, and we have done some of the reactions, knowing where the H and the OH can be added to. Okay, so for this worksheet, the last part, okay, let's push through the last part, then I will most probably end it for today after we go through this last one. I think enough for today already. Okay, so the last part really is the addition polymerization. Okay, so it's adding alkene molecules. So alkenes can add to themselves. Yeah, they can add to themselves to form long molecules, or we call it long chain molecules. Okay, or long chain. Okay, we call them polymers. Okay, so to add to themselves to form polymers, we call it addition polymerization. So what's the condition required for this? Okay, take note, the condition is not very specific here. It's just a very generic one. It is just high temperature, high pressure, and we have a catalyst. So all three, temperature, pressure, catalyst, all have high temp, high pressure, and catalyst itself. Okay, so I'm going to show you how ethene undergo addition polymerization. So in polymerization, actually, you are adding a lot of the alkene molecules together. So let's draw the basic unit for ethene first. So this is an ethene. You realize for polymerization, I draw the molecules slightly different. You realize the position of my of the bonds around the C double bond. C is actually towards the top and the bottom instead of to the top and the right. So if you look at all the previous examples, I purposely left the space below empty. Okay, I purposely left the space below empty for all the addition reaction thus far. But for polymerization, you realize I purposely left the sides empty. Okay, the sides are empty. Why is it so? You will see it later. Okay, why is it so? You'll see it later. So the equation here, okay, let's go back to doing the equation. So this single unit of ethene, I'm going to have many, many of them. That's why I put N in front. So it's a balancing equation. I put N because there's so many of them. I let it undergo high temperature, high pressure, with a catalyst. Okay, so let me draw the arrow longer. And catalyst. Okay, so in addition polymerization, the double bond breaks. Okay, think of it like two hands holding, right? One of the hands will open up and go to the side. So one of the hands will go to the side, and hence I will have it like this. So you realize I break the double bond. Okay, this is my basic unit here. Okay, I'll break a double bond. And this double bond will actually extend sideways. Okay, this double bond once broken, I'll have each carbon extend their hands to the sides. So you realize by breaking the bond in the middle, they now can extend towards the side. So this guy here can bond with another ethene to the left side, to the right, to the left side, to the right side. So in a sense, this whole thing, okay, I put a bracket N here to show you that actually to form the long chain, I just have all my ethenes side by side, and they will form that long chain, okay, when they are double bond break under high temperature, pressure, and in the presence of a catalyst. Okay, so this is actually how the reaction looks. Now, what's important is not just the reaction. Okay, you actually learn some interesting terms here when we deal with addition polymerization. You will learn this term called monomer. You'll learn this term called repeating unit. And you will learn what is the full structure formula of your polymer. Okay, polymer. Okay, need not be polyethylene, it's just general polymer. So how to identify all of this? So the monomer means single unit. Polymer means many unit. Okay, join up together. The repeating unit is just like when you do tessellation, right? It's like the repeating unit lah. So literally repeating. Okay, the repeating unit. It's like a stem that can pop, 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 pop. So what exactly is the monomer here? For polyethylene, the monomer is actually the thing that you are reacting. So the ethene is the monomer. So the compound with the double bond, okay, the one with the double bond before reaction is the monomer. Okay, I say again, the monomer, the single unit, is the one with the double bond. How then is the repeating unit? What exactly is the repeating unit? Okay, to draw the repeating unit, what I need to do is consider this. Okay, break the double bond. Okay, break one of the double bond. Okay, extend bonds. Okay, extend bonds to the side. Okay, so I'm going to show you how it looks. So how the transformation look. Okay, I'm just going to draw it out for you to show you. So this is the monomer, right? This is the monomer that I've drawn here. I'm going to break one with double bond. So I'm going to erase it out. So can you see here? I broke one with double bond, right? Then I'm going to extend the bonds to the side. So this is the repeating unit. Okay, this is the repeating unit. To convert repeating unit to the polymer, the full structural formula of the polymer, first step, you add the bracket. Second step, you add N. So the full structural formula for the polymer, what I'm going to have is literally have the repeating unit first, draw the repeating unit. How the transformation occurs, I add the bracket, I add the N. Okay, so that's how you get from the monomer to the repeating unit and then to the polymer. And of course, you can actually reverse it. Okay, so if I got a polymer, I can actually find the repeating unit by removing the bracket, removing the N. I can have the repeating unit become the monomer by removing the bonds to the side and form back the double bond in the middle. Okay, so this is the step to take to find out what's the monomer, repeating unit, and the full structural formula of the polyethylene. So we're going to do a little bit of practice. Okay, so let's go to the next slide. Now, I want you to look at this thing here. This is a segment of the polyphenol propene. Don't need to worry what this means. We just look at this thing here. This is a segment, okay, of the polymer. That's why there's no end, because just imagine it's like a long chain. It extends towards this side, it extends towards this side. But what I do is I cut it such that you only see one segment of it. So this is the polymer. Okay, so I say again, this is the polymer. Okay, this is the polymer here. Now, I want you to try now, based on this first part. Okay, sorry, let me erase all the things, all the drawings I've drawn so far. I want you from the polymer, I'm going to tell you the steps here. I want you from the polymer, do the repeating unit. Once you get a repeating unit, I want you to find for me what is the monomer. Okay, I say again, from the segment of the polymer, I want you to find for me what's the repeating unit. And from the repeating unit, find out what's the monomer. So do it step by step. Give you all from now till 2 minutes until midnight. Okay, 12 a.m. Okay, to go and try this out now. Okay, please carry on. Let me pause the recording. Okay, so how exactly to do this? First thing, for the repeating unit, identify what is a segment. Okay, what's the simplest segment that I can have? So what do I mean by that? If you look at this, do you realize there are 3 repeating segments? So you can see here, this is one repeating segment. Then there's a second one, there's a third one. So my repeating unit, okay, will look like this. And let me use red color to write. Okay, so my repeating unit is C. Then I got this weird looking hexagon thing at the bottom. CH3 on top, H at the bottom. So this is the repeating unit. Now, however, some of you may have done it the other way around. You may say, actually the repeating unit, right, instead of like this, I use this as a repeating unit. Is it okay? What's the difference between the two? You realize that one, the hexagon is on the left carbon. The other one, the hexagon is on the right carbon. Then of course, let's go back to the basic question. Repeating unit is the one that you can stem to produce the whole molecule. So looking at the green one, looking at the purple one, do you think that when you stamp the thing, you will get the same kind of big molecule? Answer is yes. Okay, answer is yes. So there is a second answer to this. If you draw this, it's correct. You can actually draw the hexagon, okay, on the right-hand side instead. Okay, but must make sure your CH3 goes around accordingly. Okay, so repeating unit, either one of this is fine. And to convert to the monomer, what I'm going to do is I'm going to remove the extension. First step, to remove bond extended to the side. Second step, I'm going to form back the C double bond C. So let's use the left-hand side one for convenience. Okay, so I'm going to do step 1 and step 2 here. So I'm going to draw the molecule first that I have. I'm going to draw like the repeating unit first. Okay, I'm going to draw repeating unit first. Okay, so what exactly does it mean remove the bond extended to the side? It means that I'm going to erase this and this. Okay, so I remove the bonds at the side. Next, form back the C double bond C, like this. So you can see here, that's how I got my monomer. So it's quite a simple step to take to get back to the original one. Okay, so based on this, okay, what you have your repeating unit and your monomer. Now, I just want to say what exactly is this weird looking stuff. What is this exactly is this weird looking stuff? Because I told your other classmates, so good for you to know. This thing here is actually called your benzene ring. What exactly, benzene ring. What exactly it is actually you got 6 carbons bonded in a hexagonal manner. Okay, the double bond is over here, over here, over here. This is H, 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 H. So it's actually a C6H6. It's quite a cool molecule here. Okay, C6H6. Interestingly, actually, this double bond will actually flip across one another. So instead of being on over these 3 sides here, it can actually convert towards the left and the right. Okay. So you can see the double bond got jumped. Okay, you're going to learn this more when you go tertiary education. For now, you're not going to learn about benzene rings, so don't need to be afraid about it. Okay. Okay, so since we're done with that, I want you all to try now part E. Okay, try now part E. The last one I'm going to ask you all to try already. So let's go. Okay, 1 minute. Quickly do it. Actually, sorry, I realized. Never mind. Don't ask you all to do it. This one, I arrange for you all first. Okay, if you look at this whole thing here, if I ask you to do the repeating unit and the structural formula, I tell you sure jialat one. Okay, so let me explain the first question first. The structural formula of organic compound X is as shown, so it looks like this. You can see here, there's a C double bond C. So this is actually where your unsaturated part comes in. You know that for it to undergo addition polymerization, your focus will be over here. So this is X undergo addition polymerization to form the polymer Y. So Y is the polymer. X, because it undergoes addition polymerization, this guy here must be the monomer. So what we have here is the monomer. Very different from what we have been drawing, because this one long chain towards the left and towards the right. Okay, so in order for us to be able to draw the repeating unit and the structural formula for Y, what's important is for us to rearrange this whole molecule. So always put your attention to the C, always put your attention to the C double bond C. So what you want is your C double bond C is in the middle. Okay, so I'm going to rearrange it. Okay, C double bond C in the middle. So I'm going to highlight it in yellow, show you that this is the part to focus on. Now, what you want is the rest of the groups to attach either to the top or to the bottom. Okay, so you realize above this first carbon, I got F on top. So that's good, it's on the top. On the second carbon, I got H on top, so that's good. However, on the left-hand side, can you see there's this big chunk over here? I'm going to highlight now in green. There's, oh no, sorry. There's this whole big chunk in green here on the left-hand side. So I'm going to take this whole green chunk to shift it down. I'm going to take this whole green chunk here, I'm going to shift it down. So, over here. Okay, so this whole green chunk is now at the bottom. And you can see on the left-hand side, it's empty already. What I'm going to do now next, I'm going to take this whole, no, wait, this is not good. Beige chunk. Okay, instead of attaching this whole beige chunk to the right-hand side of the second carbon, I'm going to shift it down and I'm going to attach it to the bottom. Okay, so this whole thing here at the bottom here is the beige chunk. So now you can see that my molecule, I can do addition polymerization because my left side and my right side is empty. Okay, my two blue side is empty, so I can definitely do my addition polymerization easily. I can visualize it better. Okay, so the rearrangement is actually for better visualization. Hence, the repeating unit, how to get from monomer to repeating unit. What you need to do is, step 1, break double bond. Second step, extend bond to the sides. So I'm going to draw that whole chunk here again. Then I'm going to draw that whole chunk here again. Okay, I'm going to condense the whole thing here. So this is actually a CH3. So I'm going to put a CH3 at the bottom. I'm going to condense this whole thing here. This is going to be a CH2. Okay, this is going to be a CHO. Okay, CHO. So I condense the whole thing to like this so that it's easier for us to see and visualize. So what I'm going to do here, this is my monomer. This is not my repeating unit now. So my monomer, in order to become a repeating unit, I have to break the C double bond C. So I have to break one of the bond. Okay, break one of the bond in C double bond C. Then I extend the bonds to the sides. So this is my repeating unit. Now for the structural formula of Y, I'm going to do something. Okay, I'm going to say draw at least 2 repeating unit for the structural formula. Then say, Archer, structural formula draw at least 2 repeating unit. What do you mean? So this is the repeating unit, right? Normally to form the polymer, I already said to add the bracket. That's the first step. Second step, you add the end. Correct? So instead of straight away like this, I'm going to have a step 0. I'll add one more repeating unit. So how does it exactly look? Because I want to draw at least 2 repeating units, so I'm going to draw 2 times of this. Okay, so first repeating unit that I'm drawing. So this is the first repeating unit. I'm going to draw the repeating unit one more time. Then I'm going to add the bracket. Then I'm going to add the end. Okay, so that's how you go about doing this. Now, of course, you need a bit of practice lah. So this is where we're gonna do the final practice, okay, final practice. So let's go to slide 23. Okay, you have this 7A, 7B, 7C. Okay, I want you to draw a line over here. Instead of straight away jumping to the polymer, I want you to first draw for me the repeating unit. Okay, before you hit to the polymer. Second thing, I want you to take note, C, you need to rearrange it a little bit. Okay, because there are 3 questions here, and this is our final practice, I'm going to give you all 5 minutes to just complete A, B, and C. Okay, once we are done with this, we are actually done for today. Okay, so let's carry on. Okay, take the next part to just try it out. We're recording the final part now, so I hope you are already done with this. Okay, so I'm just going to go through it. So the way to find the polymer is to, from the monomer, get to the repeating unit. From the repeating unit, get to the polymer. Okay, it's quite a simple step. So we already mentioned a few times already, from monomer to repeating unit, you're going to break one of the double bond, okay, one of the bonds in the double bond, and then you're going to extend the bonds to the side. So this one here, the repeating unit will look like this. So you can see here, by drawing this, I've actually broken one of the bonds in the double bond, and then I'm going to extend the 2 bonds to the side. So this is the repeating unit. The polymer, okay, would then be this. Okay, however, if let's say I want 2 repeating units at least, so I'm going to draw one more of this. So let's say, assuming the question wants me to draw one more repeating unit, then it will look like this. Okay? So this one here is where I will say that there's at least 2 repeating units. Okay, of course you can draw 3 lah, and 4 repeating units are up to you, but you just have to answer the questions. Okay, make sure that if they say at least 2 repeating unit, then make sure you have at least 2. You write 3, you write 4, I have no issues. Just that you're wasting time by drawing more lah. Okay, next one, part B. So I'm just gonna quickly do it now. So break the double bond. So I'm just going to draw with the double bond broken. Then extend the bond to the side. So this is the repeating unit. The polymer, let's say now I just want a single unit. I don't need 2 repeating units. Just a single repeating unit will do. So this is how the polymer would look. Okay, I hope you're getting a hang of it after going through together. The last one actually requires you to rearrange a little bit. Okay, so as I mentioned, whenever you need to rearrange, your focus should be on the double bond. Okay, the left and the right hand side of the double bond should be empty. Hence, I'm going to take this whole chunk. Sorry, let me highlight instead of. Sorry. I'm going to take this whole chunk here. Oh, sorry. I'm going to take this whole chunk over here in beige. This whole chunk. Oh no, I'm using the wrong color. What's wrong with me? Okay, this whole chunk here, I'm going to shift it down. So, first thing after rearranging, okay, after rearranging, it will now look like this. So you can see the sides are empty now. Hence, it's easier for me to draw my repeating unit. And you realize this thing over here, this group over here, can actually be condensed into a CH3 group. So this is my monomer. So after rearranging, you'll get this. And from this monomer here, I'm going to convert it to a polymer. So I'm going to break one of the I'm going to break one of the double bond. Okay, so I'm going to draw the same thing, but I'm going to break one of the double bond. And I'm going to have the bonds extended to the side. The polymer will just be having the bracket with the end. So draw the repeating unit once again. Then I draw the bracket and have the end over there. Okay, so this will be the end of worksheet 5 extra. Okay, so we're actually done with worksheet 3, 4, and 5. So let's just double check. Let's go back to slide 20, I think. Okay, slide 20, we actually covered all the way here. 21, all the way to the bottom. So we ended worksheet 5 already. So let's go back to slide 19. Sorry, not slide 19, slide 18. So we have actually done the last part. Okay, the last part of this whole worksheet 5 is actually number 7, which is on addition polymerization. Okay, a lot of drawing, a lot of working through, but once you have worked it through, actually it's a lot easier to understand what's going on in the whole equation here. Okay, so we are done until slide 24, no, 23. Okay, we're done this slide 23 already. I'm not going to go through 24 onwards. So this will mark the end of your worksheet 5. Okay, I'm going to stop here. Let me stop my recording as well.